I want to check the accuracy of the lead screws on my CNC router. And for that I could use one of these cheap linear encoders. And I already figured out how to read those from a Raspberry Pi because I got two of those on my XY drilling machine right here. And I'm already reading that in with this setup here. But I don't know how accurate these are, so as a backup I want to also measure it with digital calipers, and these all have kind of a digital interface right here. So I got hooked it up to a Raspberry Pi. So to open these up, you have to peel the sticker off the back to get the screws out. I've already taken all the screws out of this one. And here's the main circuit board, and I don't know of a connector to go on these, so I'll just solder some wires on there. And probing the signals on this one, it periodically sends out two 24-bit words via synchronous serial at 76 kilobits per second. Now, other digital calipers send something a bit simpler than that, but I like how these ones work, so I'll focus on this one for now. And not all digital calipers have this handy thing that you can pop off to get at the contacts here. This one here, for example, has just a solid piece of plastic, but if I look in where the battery is, I can see just the ends of those four pads which are present, so I'd have to cut a hole in the plastic to put wires on this one. Now these calipers only use 10 to 15 microamperes. The problem is, even if you turn them off, they're still on, so they drain their battery in the space of about a year, which is why I don't keep batteries in them normally. So for this, since two of the wires go straight to the battery, I figure I might as well give it power from the Raspberry Pi. So I just used 3.3 volt from the Raspberry Pi, divided that in half with two resistors, and that powered the calipers just fine. But I couldn't read the signal from the Raspberry Pi because logic high for the calipers was 1.5 volts, and anything below 1.8 volts on the Pi is a 0. So what I need is something to level shift that to basically 3.3 volt logic levels so the Pi can read it, but that's complicated. But then I thought, why don't I just offset the voltage so that the output from the calipers straddles the 1.8 volt 10 threshold in the Raspberry Pi. So I used this series of resistors so that the 1.5 volts exactly straddles the 1.8 volt threshold on the Pi. And I soldered those resistors onto the header that plugs into part of the Raspberry Pi's 40-pin GPIO connector. And I don't have a picture of all the resistors shown connected because I added heat shrink tubing as I went. I couldn't add it afterwards. I got this one hooked up to a Raspberry Pi 4 with the scope probes on it too. And this is synchronous serial, and that means we have a clock line that tells us where the bits are. And here's the bit stream. And if we zoom in on this a little bit, what we can see is that the data line, that's the yellow line, only ever changes while the clock is high, which tells us basically the data valid period is when the clock is low. So every time the clock goes low, we should read the bit value. I wrote a short Python program that keeps reading a clock line, and when it goes low, reads another bit and decodes that, and that works, giving me the values that are on the caliper, 14.71, indeed 14.71, move it a bit, 6.88, 6.88. But the problem is at 76 kilobits per second and using Python, my Raspberry Pi 4 is just barely fast enough to keep up with it, and sometimes it slows down after a while and then it starts failing consistently. But on this machine I've only got a Pi 3, which is only half as fast, so I ended up re-implementing the whole program in C, which is about 100 times faster than Python. So it sends a 24-bit value, and I worked out that is in 2480 per inch, and that works out to 0.00124 millimeters per increment, whereas the display resolution is only 0.01 millimeters. So we effectively have 8 times higher resolution on that digital output. And the second 24-bit value that comes out is also positioned in the same resolution, but it's kind of an absolute value in that it doesn't clear if I zero the calipers. It stays the same, but it still kind of resets if I power off the calipers, as in remove power. But when it comes back up, that value modulo 5 millimeters will still be the same because the sensor kind of repeats every 5 millimeters, so it gives me the absolute position within a 5 millimeter range. And so if I do an experiment that just measures long-term creep, even if power failed for the whole experiment, I still have that value, and as long as my creep between readings is, say, less than 2 millimeters, I can always tell which way it went. So that's actually a really cool feature. But back to this machine, once I turn on the servos, and they're on right now, you can hear the buzz from just them always doing PWM to control the servos. Then I couldn't read these calipers at all because the servos caused so much electrical noise, there was just too many glitches on the line. So then I tried just hooking up ground to the caliper's ground, and that didn't work because these actually connect plus to ground, they're positive ground, and even then the negative ground isn't the same as ground either because it's voltage shifted. Then I connected ground through a 0.1 microfarad capacitor to deal with the offset, and that helped a lot. But it was still not reading reliably. So I ended up implementing debounce logic in the code, and I even count how many glitches I've got, and it's actually quite a lot, but it decodes the values quite reliably even with the glitches. Of course, this would be better solved by putting some small caps on the clock and data lines to filter them a bit, but this solution works for now, and it's only an experiment. So looking at the integer values coming out of these are in increments of 1.25 microns. I figure even if they jump around a little bit, if I average a bunch of those together, I should be able to get readings that are clean and precise to the micron. So with a caliper close to 0, I read it for 2,000 times and then plotted those values, and that's the line in blue, and it seemed to jump up and down a bit. So the yellow is averages of 7, and indeed it seems to jump between two different levels. So not exactly the Gaussian distribution I was hoping for, so averaging, say, 16 samples isn't going to help very much at all, because I might be in a high period or a low period, and the difference between those two is 6 microns, or just a little bit less than the resolution of the display. But thinking about it some more, if I just average a long enough period, say for instance from here to here, then I get a sense of how much of the time it's more on the high side versus how much is on the low side. And I can still get a reasonable average to figure out where I am in between those. It's just that means acquiring about 400 samples, and that takes 2 minutes. So I can still get micron resolution out of these calipers. It just has to be a very slow-moving experiment. And comparing this with my linear sensor, which I can only read to 0.01 millimeter, they seem to fall consistently within about that. So they really are 0.01 millimeter accurate, which is actually kind of impressive. Now, these two use the same protocol, which I find much more interesting, although it's a bit harder to read, but it gives me that extra precision in the absolute value, whereas these two just send a single 24-bit value every time, and that's encoded in 0.01 millimeter increments. And so they're not as useful that way, although this one sends the value about 10 times a second, which is very useful, whereas this is 4 times a second, and these ones just 3 times a second. This linear sensor sends it 9 times a second, which is also very nice. So for experiments, these are very useful. Although if you're trying to build it as part of a machine, I'd recommend going with something like these. These work exactly the same way as the calipers, cost about 2 or 3 times as much, but they're just a little bit more reliable. They run on 3 volts, so much easier to hook up to a Raspberry Pi too. And I put my code up on GitHub, so if you want to use that, just keep in mind not all calipers talk the same protocol. You'll have to scope it out.